Hello! In today's video, we are diving into a common challenge faced by many desktop CNC users, the noise. Because CNC routers are great tools to have in a workshop or at home, but they make an awful lot of noise, and most of them don't come with an enclosure. Protecting your ears is really important, and while wearing acoustic protection is the easiest and cheapest way to go, it is not always convenient, and it doesn't attenuate the sound for neighboring spaces and people. On one side, if your CNC is small enough, adding an enclosure is possible in order to attenuate the sound. There are some ready or almost ready-made enclosures available online. Unfortunately, dimensions, soundproofing effectiveness, dust collection ports and wire management may not fit your needs. So many of you may end up having to make their own custom DIY enclosures. On the other side, if your CNC is quite large, then an enclosure might not be the way to go. In this case, one way to reduce the noise is to make acoustic treatments near the CNC and to your workspace using acoustic panels. But those kind of panels can also be used in your office, your home or home studio to reduce annoying reverberations and improve the feel of those spaces. For my part, I have a CNC which is small enough to get inside an enclosure, but too large for an off-the-shelf enclosure, so I will need to make one myself. And my initial questions that you are probably also asking yourself is, what materials should I use and what results will I get? Most other CNC enclosure videos I have seen on YouTube don't really tell you the design rules to size and predict the attenuation of an enclosure. They show you a custom build and their custom result, which is great because they share it, but they don't detail the why. So in this video, I am making a review of this problem of acoustics. I am showing you the metrics that are needed to predict the attenuation you can get from an enclosure and discuss the different materials you can use. I summarized it and share it with you so that you can save some time and make the appropriate choices for your own soundproof CNC enclosure and for acoustic panels. Note that there is no right or best way to soundproof your desktop CNC, because it depends on your space configuration, on the kind and cost of materials you can purchase, and on the ease of implementation. Just take the time to watch this video and understand the underlying concepts, and you'll be fine. Also remember, reducing the noise will make it much more enjoyable for you to work with your CNC. And not only more enjoyable, because besides the obvious annoyance, long exposure to high levels of noise can actually be detrimental to your health. It can lead to increased stress, fatigue, and even hearing damage over time. So that's worth taking some time to make it right, isn't it? You can find in the description a list of the chapters so that you can jump to a specific section. However, I would encourage you to watch the whole video. First, I'll review the physics of sound and tell you how to deal with the units. Then we will see how to estimate the attenuation from one panel by introducing two laws, the mass law and the mass spring mass. We'll see the attenuation for a combined panel, for example when there is a window. From that, you can also calculate the attenuation of a full enclosure. After that, we'll see the insertion loss obtained by the enclosure. That is, the effect when you put an enclosure around a noise source. We'll see the effect of absorbing materials, such as foams, and how to average their effects. And finally, for the enclosure, we will see the effect of leaks and how to deal with the openings for temperature management. In a second part, we'll see details about materials and a possible implementation. Then I'll cover quickly acoustic panels. Those are the elements you need to know to make you feel confident that you are going to make an informed choice for building your enclosure or treating your workspace. So let's start. To know how much we need to improve, we have to talk some metrics to see where we start from and where we're heading. Sound is a vibration of atoms that propagates as acoustic waves, a periodic change of the local density, that is, a succession of compression and rarefaction, whether it is gas, solid or liquid. We can describe a single tone sound by its amplitude, its frequency and its wavelength. The amplitude, which is a deviation of the local density to the ambient atmospheric pressure, is the sound pressure and the unit is in Pascal, noted PA. It is the international derived unit for pressure. It is a unit you may encounter when looking to buy a microphone, where they indicate a sensitivity relative to 1 volt per Pascal. The time between successive states on a single tone sound is the period. If you take the inverse, you get the frequency in Hertz, which is the number of cycles per second. The human ear can listen to sound with a frequency from 20 to 20 kHz. The wavelength is a dimension in meter. It is given by the equation V over the frequency, where V is the speed of sound in air and is about 343 meters per second. So, a tone at 100 Hz has a wavelength of about 3 meters, 500 Hz is about 69 centimeters, and 2500 Hz is about 14 centimeters. As we'll see later, the wavelength has an impact when it is proportional to a multiply of a dimension of an object or of the space between objects, for example, of a room, a panel. Now, sound is a combination of different frequencies and amplitudes. A microphone converts the pressure level to an electric signal. And you can get a waveform dependent on time. It is possible by applying a mathematical transformation to this waveform, called the Fourier transform, to separate a waveform into its frequency components. And you get a graph which gives you the amplitude for each frequency of the sound it contains. You will find material properties and attenuation displayed on a frequency spectrum. Here I show a simple signal for those of you who might not be familiar with this. In this example, there is a signal composed of a sine wave at 500 Hz and one at 3000 Hz. If you apply a Fourier transform, you get the frequency spectrum, which consists of two peaks which correspond to the two components of the signal. The lower horizontal axis is on a logarithmic scale. A minor division represents a multiplicative factor of the adjacent major value. On this example, you see 100, 200, 300, 400 and 500 Hz. The amplitude of the 500 Hz signal is 1. Then the next major value is 1K, so you have 2K, 3K. The amplitude of the 3000 Hz signal is 0.5. The sound emitted by a CNC depends on many factors, among which the spindle speed, the number of flutes of the tool bit, the kind of material being processed, its shape and the vibration in the CNC frame and spindle. For example, a CNC with a spindle at 12,000 RPM will have a peak amplitude near 200 Hz. If the tool bit has 2 flutes, there will be a peak at 400 Hz. If it has 3 flutes, the peak will be at 600 Hz. Then you have harmonics at multiples of those frequencies, but with lower peak values. The rest is sound produced by the vibration of the stock and of the CNC frame. Now, on this graph, the vertical axis is not in volts nor Pascal. It is in decibel. This scaling is needed because the amplitude of sound does vary greatly. The minimum pressure difference a human can hear is 20 micropascal. A normal conversation is near 20 millipascal, so 1000 times more, and loud noises are in pascals or tens of pascals. Given the amplitude of sound, when making a measurement of a sound level, because the pressure variation is so large between a sound which is almost inaudible and a loud noise, we take the ratio of a reference pressure and the measured pressure, and by doing so the units cancels, so it is no more Pascal, and we use a logarithmic scaling to make the number easier to read. It is called the sound pressure level and is expressed in decibel. Usually the reference pressure is the minimum pressure a human can hear, so 0 dB is the minimum pressure you can hear. The previous graph is the sound pressure levels over the audible frequency range. Often you'll have a single number for the sound level because the amplitudes are in this case average at all frequencies. For reference, here is a scale of sound pressure level. As I said, the threshold of hearing is 0 dB. Near 30 to 40 dB is about what you find in a quiet bedroom. 60 dB is a normal conversation at 1 meter. 60 to 70 dB is what we could consider the beginning of the noisy region. Power tools are in the 100 dB area. From 70 to 90, if exposed for a long time, you can start to have temporary hearing damage, and above 90, you can have permanent loss of hearing. Because sound pressure level is on a logarithmic scale, noise source in dB cannot be added directly. For example, a CNC making 80 dB of sound placed next to a vacuum cleaner at 80 dB do not make 160 dB but 83 dB. If you want to know the sum of multiple unrelated noise sound, you need to use this equation. L1 to Ln are the sound pressure levels of the different sources, and L total is the resulting sound pressure level. The quick reference values displayed here show you how the sound pressure level is increased when you sum two sources. We see again the previous example. When two sources are equal, the extra dB is 3. When there is more than 10 dB difference, the less noisy source has almost no impact. Now we saw that above 70 dB is noisy. The annoyance level, on the other hand, really depends on the noise floor of your environment. But it can be really low. 50 dB and even 40 dB could be annoying. If you're in a bedroom that is 30 dB and a noise source makes it 40 dB, then it is 10 times noisier than the base level. Annoyance is about human perception, and as a matter of fact, the human ear is not sensitive equally to all frequencies. So the sound pressure level can be expressed by weighing to take into account this effect. It will be denoted dBA or dBc on a sound meter. This plot shows you the difference between the two references, where A weighing is a reference for human ear. Those curves show the attenuation which is applied to measurements before averaging. So to make or use measurements correctly, you need to know which weighing to use or was used. Now, to interpret correctly sound pressure level measurements, you need to take into account the distance from the source at which the measurement was made, and also the environment around the noise source and the measurement device. The sound propagates as spherical waves. If you take a CNC in free field or inside an anechoic chamber in a lab, which makes the same effect as free field due to the wall shape and materials, the sound pressure level is reduced by the inverse square law. It states that the sound intensity decreases by a factor of 4 or 6 dB each time you increase the distance by 2. The sound meter measures the sound coming from one direction only. However, if it is not free field, then it is not the inverse law. For that, we have to see how sound interacts with the environment. In sound waves, the atoms have extra energy due to the sound-induced vibrations. They more or less lose part of this energy when they come into contact with different types of materials. On some materials, the incoming sound wave will be more reflected, that is, the transmitted energy is low and the reflected energy is high. On other materials, the incoming sound wave will be more absorbed, that is, the transmitted and reflected sound waves will have smaller energy because more energy will be absorbed within the material. To absorb sound, that is, to dissipate sound energy, the vibration of the atoms must be reduced by causing collisions with materials that convert part of the collision energy into heat. The energy loss can occur directly from impacts or through larger scale deformations. In the case of deformation, the pressure gradients induced by the sound waves induce forces in various directions, leading to material deformation and subsequent energy loss. To simplify, if a material is hard, dense, heavy and rigid, the sound will primarily reflect off it. On the other hand, if the material is soft, porous and lightweight, the sound waves will propagate through it, losing energy in the process. Later in this video, when we discuss enclosure materials, we'll examine the densities of these different types of materials. There are two primary metrics used to describe the behavior of a material interacting with sound. One is the absorption coefficient. This represents the ratio of the absorbed power and the incoming power. It is noted alpha and its value ranges from 0 to 1. A lower value indicates that the material is more reflective, while a value closer to 1 means it is highly absorbent. The other one is the transmission coefficient. This is also a ratio between 0 and 1, measuring the proportion of sound energy that passes through the material. However, for transmission, it is more often expressed as a logarithm, and it is called the sound reduction index or transmission loss, and is expressed in decibel. The transmitted sound pressure level is calculated as the incoming sound pressure level minus the transmission loss. We saw that decibel do not add, but in this case, when you are using attenuation, you can add or subtract dB. Getting back to the CNC example in free field. If it is now placed inside a closed room with reflective walls, floor and ceiling, the measured sound level will be higher. It does not decay anymore following the inverse square law. It is because the sound meter captures not only the direct sound from the source, but also the reflections from the room's surfaces. This includes the direct pass, the first-order reflections, second-order reflections, and so on. In a room with very low attenuation, the sound field becomes diffuse rather than free field. Here, the sound pressure level remains relatively constant throughout the space. To attenuate the sound reaching you in such an environment, you need to either block the sound or absorb its energy. If your CNC router is too large to have a reasonably sized enclosure, you can use personal equipment to protect yourself. However, this won't address noise exposure for others in adjacent rooms. In this case, installing acoustic panels on walls and ceilings can help absorb a portion of the sound energy. If the CNC is smaller, then you can use an enclosure. You can also combine the enclosure with additional acoustic treatments to further reduce reflections and improve the acoustic environment. Making good attenuation with an enclosure combined with acoustic improvements to your workspace is what will make you a more enjoyable and productive environment to work in, even when the CNC is not in use. Now let's dive deeper into the details and metrics. Very accurate acoustic modeling is complicated. It requires expensive softwares and having the detailed physical properties of all the materials. However, it can be approximated so that you can estimate the order of magnitude of the attenuation you can get. And the goal anyway is not to become an expert or make ultra-precise calculations. The goal is just to know enough to make reasonable decisions, make realistic approximation and be able to evaluate if an isolation implementation matches its expected performances or if there was a defect in the making. There are two laws that you need to be aware of: the mass law for single-leaf walls and the mass spring mass for multi-leaf walls. I'll begin with a quick summary of the two so that you get a first side-to-side comparison. For mass law, when the frequency increases by 2, the ratio between transmitted and incoming energy is divided by 4, that is 6 dB. For mass spring mass, when the frequency increases by 2, the ratio between transmitted and incoming energy is divided by 16, that is 12 dB. From this, you may think that you have to go for the multi-leaf. Well, yes and no, because attenuation in multi-leaf is better in high frequencies, but it can be lower in the low frequencies. Furthermore, it can be more complex to build correctly. We have to see the details of each law to see how it impacts the attenuation. The mass law states that the transmission loss from a single rigid wall is dependent on the mass per unit area and the frequency. The equation is as shown. ms is the mass per unit area in kilogram per square meters, and f is the sound frequency in hertz. You may see other values for the second part, depending on the incidence angle considered for the sound wave. It is not a problem. Here, we just want the general trend. We see that when the frequency is doubled, the attenuation increases by 6 dB. A doubling of the frequency is referred to as an octave, so we can say that the attenuation increases by 6 dB per octave. And when the mass is doubled, the attenuation is also increased by 6 dB. For example, here is a plot of the transmission losses obtained from the mass law for two acrylic panels of 3 and 6 mm. This basic equation takes only into consideration the effect of inertia. It is simple, but it is a good approximation for the middle frequencies. Let's compare this mass law with real measurements. These measurements were made by Icoso and al. They made measurements for 3, 5 and 15 mm acrylic panels. First, I'll show the results for 3 and 5 mm, and we'll see the 15 mm later. In the mid-frequencies, we see that, as expected, it is in good agreement with the simple mass law. To be more complete, sound propagation and attenuation not only depend on mass but also on stiffness, damping and dimensions. And in this case, a more complete plot would look like that. You have the mass control area in the middle, which follows the 6 dB per octave trend. Then you have the effects of stiffness and resonance at low frequencies and the effect of coincidence with the critical frequency at higher frequencies. In those regions, there are dips which correspond to losses of isolation. Those dips are more or less important depending on the damping factor of the material. Coincidence occurs when the wavelength of the sound wave equals the wavelength of the bending wave of a panel. This happens at what is called the critical frequency. The critical frequency can be estimated with this formula. It depends on the speed of sound, the density, the Poisson's ratio, the Young's modulus and the thickness. As you see, the critical frequency is inversely proportional to the thickness. And we see a first issue. You may want to increase the thickness of your panel to increase mass, but the critical frequency will lower. You see on this plot the evolution of the critical frequency depending on thickness for plywood, MDF and acrylic. For acrylic, at 15 mm, we see a 2.5 kHz critical frequency. If we go back to the measurements and add the results for the 15 mm panel, we see the dip that was expected near 2500 Hz. An 18 mm MDF panel, sometimes mentioned in videos and forums, has a critical frequency near 1.2 kHz. For instance, if you consider a powerful CNC with a spindle at 24,000 RPM, which translates to 400 Hz, with a 3-flute tool bit, the resulting noise peak would occur at 1.2 kHz, right in the dip caused by the critical frequency of the MDF panel. In this example, those thicknesses of acrylic give a mass per unit area of 3.5, 5.9 and 17.7 kg per square meter. Now you see the effect of the mass law. Although it is almost double the mass, the 5 mm curve is not much above the 3 mm curve. Intuitively, you could expect to have almost twice the attenuation. To simplify, if we consider 3 and 6 mm instead of 5, to have a factor of 2, that makes 3.5 and 7 kg per square meter. If we compare the attenuation at 400 Hz, we see 16 dB and 22 dB. However, if we consider two panels of 3 mm, it gives 32 dB. It is true if the panels are far enough from each other. If so, they are decoupled. However, when they get closer, they become coupled and interact with each other. This is where we enter the mass spring mass law. When panels get closer, the air or insulation in between the panels act as a spring. The frequency response of the material is different. For the sake of clarity, I present just the trends and merge the dips of the individual panels. So approximately, there is a dip at the resonant frequency F0, then the attenuation increases by 18 dB per octave, then raises by 12 dB per octave. Then there are the dips due to the critical frequencies of panels that, as I said, I represent as one dip. You see that, as I mentioned in the brief overview, although it gives higher attenuation at high frequencies, it can be less effective at low frequencies. The choice then depends on which kind of sound you want to attenuate and also on the build complexity. Now, an enclosure may not be made all of the same material. For example, if you have a window on one side of your enclosure, the resulting transmission loss coefficient can be calculated as follows. For example, your panel has a 30 dB attenuation and your window is 10 dB. The resulting transmission loss is 16 dB. And you may also do that for the different panels of your enclosure. The bottom may not be the same as the sides and top. Now that we've explored the attenuation provided by a single panel and how to calculate the attenuation from a combination of panels, let's consider the insertion loss of a full enclosure. As mentioned earlier, enclosing a noise source increases the sound level inside due to internal reflections. This phenomenon reduces the transmission loss, which is instead represented by the insertion loss of the enclosure. The simplified formula for calculating the insertion loss is shown here, where R is the transmission loss of the panel and alpha is the internal absorption coefficient. The insertion loss of the enclosure decreases when the interior lacks sufficient sound absorption. For example, if you have a noise source emitting 80 dB and it is placed inside an enclosure with an internal absorption coefficient of 0.1, the sound pressure level inside of the enclosure rises to approximately 90 dB, while the level outside is reduced to 70 dB. Now let's consider adding an absorbing layer inside the enclosure. If 50% of the interior surface is covered with a perfect absorber, the internal sound pressure level drops by about 7 dB, and the external sound pressure level is similarly reduced by 7 dB. However, the benefits diminish as the coverage increases. Adding another 40% coverage reduces the sound pressure by only an additional 2.5 dB. So it is a rough approximation. It is to emphasize that the noise inside an enclosure is higher due to reverberation, and this also demonstrates that while absorption improves the enclosure's performance, its effectiveness reaches a point of diminishing return as coverage approaches 100%. The key is to find a balanced approach to absorption and other noise reduction strategies. Let's now talk about absorbing materials. As for the sound and the transmission loss, the absorption coefficient depends on the sound frequency and thickness of the material. However, to have a single number easy to use, you have to apply some kind of averaging. When looking for an absorber, you may find different averaging like NRC, SAA, alpha. The NRC number, noise reduction coefficient, averages at 4 frequencies: 250 Hz, 500, 1000 and 2000 Hz. The SAA number, sound absorption average, averages at 12 frequencies between 200 and 2500 Hz. The alpha W number averages at 21 frequencies between 250 and 4000 Hz. Here is an example of acoustic foam material. You can see that thickness is important to get good absorption. Once you have chosen the average values for your materials and thicknesses, you can get the combined absorption coefficient with this equation. Then, The two last parameters, which are also important for sound insulation, are air tightness on the parts, which can be airtight, and decoupling. Openings in an enclosure produce losses of insulation. The transmission loss, taking into account the leak surface, is given by the following equation. We see that a small leak surface of 1% can lead to a loss of 10 dB of attenuation. You are expecting 30 dB and you get only 20 dB. However, CNCs and vacuum cleaners can generate a lot of heat. So there is a need for openings for fresh air intake and hot air exhaust. The area needed can be quite important. Although that would create large drop in transmission loss, this effect can be largely attenuated by using baffle silencers. They consist of long channels covered with thick absorbing material. If you allow a large air gap, it contributes to low frequency absorption. If you have thick material and small air gaps, it will absorb both low and high frequencies. If you are limited in length, you may use more complex shapes. The last element to see is decoupling. Sound also propagates through vibrations, so you may want to be careful, when possible, to decouple the different structure elements. For example, when fixing a panel to a frame, you can increase the complexity from no decoupling to multiple decoupling elements using rubber so that the vibrations are attenuated through direct contact or through the screws. To summarize the first part, we can review the 4 key factors for making a good acoustic insulation. Those are mass, damping, absorption, and decoupling, in which I include air tightness. Let's now review the materials that can be used for an enclosure. I'll categorize materials into 3 groups: reflective, damping, and absorptive, and list their densities for reference. For reflective materials, we have some wood-based materials, plaster, acrylic, and metals. These materials tend to reflect sound waves due to their hard and dense surfaces. In the damping category, we find materials like MLV, which stands for mass-loaded vinyl, and bitumen foils. These are heavy yet flexible materials that prevent vibrations from propagating, unlike rigid materials like steel or aluminum. A mix of cork and rubber provides both damping and some absorption, so I'll classify it under the damping group. For simplicity, I'll refer to this category as heavy loads. Finally, for absorptive materials, we're looking at much lower densities. Typical acoustic foam, for example, has a density of around 10 to 20 kg per cubic meter. And, as we've seen, to achieve effective sound absorption, you need thick layers of these materials to trap and dissipate sound energy. So, for a DIY enclosure, we've learned that we need to focus on mass, damping, and maintaining a high enough critical frequency to avoid resonance issues. Using a composite approach for the panels combining reflective, damping, and absorptive materials can help meet these requirements effectively. Damping can be achieved by using heavy load materials combined with a thin but rigid backing panel. For instance, MDF and MLV can be used. A 5 mm MDF panel provides the necessary rigidity while also adding mass and keeping the critical frequency higher. Then, to isolate the MLV, further enhance the design and improve the enclosure's appearance, a 3 mm HDF panel with a wide backing on one side can be added as the outer layer. Then, in the inside, an acoustic foam can be used to provide absorption. One important point to keep in mind when constructing composite panels is to avoid making them symmetrical. Symmetrical panels design can lead to pronounced resonant dips, which could undermine the soundproofing performance. So, if we compare an 18 mm plywood panel with this composite approach, we have about 11 kg per square meter for the plywood and 14 kg per square meter for a total thickness of 11.5 mm for the composite. So if we consider only the mass low, it would only be a little beneficial as we see on the graph. But due to the composite approach, we can estimate that it should be better, somewhere between the mass low and the mass spring mass low. It is what we will verify in a future video when we build a custom enclosure. Now let's explore how to implement acoustic treatments. There are already great videos on YouTube that show you how to make acoustic panels, an example of how to treat a workshop. I give you the links in the description. For example, Linus Tech Tip used acoustic panels from Elgato. Those panels are 47 mm thick, are made of dual density types of foam, and they include an air gap on the attachment side which provides improved performance. There is a rule of thumb which states that you need to, on average, to treat 15% of a room to get good reverberations attenuation. In their video, he and his team covered less than 15% of their workshop walls, but already saw the impact on absorption. And what's interesting is that they made accurate measurements using a dodecahedron speaker, a calibrated microphone, and Room EQ Wizard to generate the frequency sweep. They show the results of their treatments step by step using the RT30 metric. RT stands for reverberation time and 30 is the attenuation in dB. So the RT30 is a duration in seconds until the reverberation is attenuated by 30 dB. However, their primary concern as content creator was to improve the quality of their audio recordings when they shoot videos in their workspace. So they didn't show what kind of attenuation they got concerning machinery noise. Nonetheless, it probably helped. Furthermore, the panels they used come at a price. These panels definitely find their place in some applications, especially in recording studios or home offices. But you may find less expensive foams in case you need higher coverage and higher efficiency. So, when treating a workspace, if your primary concern is noise absorption, larger acoustic panels made with thicker absorbing materials is probably the way to go. And in this case, you may check the videos from Alexander Chappell, who documented the process of treating his workspace. He started by covering sections of his wall with hexagonal acoustic tiles made from bare dense fiber insulation slabs. Later, he constructed his own acoustic panels and covered large portions of his ceiling. He got great results and he described that it feels really nice and that it feels much more comfortable to be in the space. For his ceiling panels, he built sturdy wooden frames and used thick mineral wool, approximately 100 mm thick. While this method is both durable and efficient, it does come with some downsides. The panels can be quite heavy, and working with mineral wool requires extra precautions due to its potential health hazards. On the other hand, for a lighter and safer alternative, I recommend checking out the video by In The Mix. In his video, he demonstrates how to make lightweight acoustic panels using a simple wooden frame, thin MDF panels on the sides, and recycled denim as the absorbing material. This approach is not only more manageable in terms of weight, but also eco-friendly and easier to work with. He seems to be using two slabs of 45 mm, so a total of 90 mm of recycled foam and fabric, which seems to be in the density range of 30 to 35 kg per cubic meter. Now, the straightforward way to place the acoustic panels is to mount them directly on the walls and ceiling, because it keeps these extra elements out of the way. But they can also be placed differently depending on your workspace configuration. As a matter of fact, usually to calculate the reverberation time of a room, you take into consideration the total surface of the room's walls. By placing acoustic panels with hard backing close to the noise source, you effectively create a virtual room with a reduced surface area, hence the equivalent percentage of coverage will be higher, enhancing the acoustic treatment's effectiveness. If your acoustic panels don't have a hard reflective backing, you can improve their performance by leaving a gap between the panel and the wall. This is because sound wave velocity is zero at the wall interface, and energy dissipation is maximized where air particle velocity is highest. By allowing a gap, the air particles have more room to move, increasing energy dissipation and improving sound absorption. While you can also improve performance by increasing the thickness of the absorbing material, this approach adds weight and cost. Creating a gap behind the panel is a more cost-effective and lightweight alternative worth considering. One final note, in custom-made acoustic panels like the one described, if you have the access to different absorbing materials, you may mix the material densities like Elgato does. For example, mixing one 40 mm of natural fiber at 40 kg per cubic meter and recycled denim at 20 kg per cubic meter. And for example, you could add MDF and cork backing if it is intended to be far from a wall. That's about it for this video. I hope you found it interesting and that it is going to help you with either your enclosure or with your acoustic treatments or both. We'll see more practical aspects and results in a future video when I'll detail the build of my own CNC enclosure. If you have made it up to this point, thanks a lot, because watch time is an important metric for the YouTube's algorithm, and people watching the entire video do help the future growth of this channel. So, thank you again for watching. And if you want to help further, please consider also subscribing, putting a like and sharing. So take care, have fun, and see you next time.